Hello, this is Dr. Viv again. I said I'd completed the multiple choice portions in the previous video, but actually this one problem had been left out because of all the space used up here. I thought I'd finish this also. Well, I have to still do this. So let me just start by doing this first. The principle used here, initially this is rotating and that's not rotating, and it's been plopped onto that, and now we have to find the common rotational speed of the entire system. So what you have to do here is use angular momentum conservation. The initial angular momentum equals the final angular momentum. So I initial omega initial equals I final omega final. Well, that gives me I times omega, because initially the angular velocity of only this was moving. And that's going to be fine. At the end, all of these two objects are going to be stuck together. So it's going to be I plus 2I, or 3I times omega f. And that tells you that omega f is omega divided by 3. So that's the right answer there. And that finishes our multiple choice part. Let's do the long problem for this. The first one is integration, and I have actually worked out all the algebra beforehand, so I don't spend any time inputting numbers in the calculator. Unfortunately, there's a little bit of an ambiguity here. It says L over 5 in the text and L over 3 in the figure. I'm just going to use the figure as my guide. So the first order of business is to draw the mass element. Now the mass element has got a width of dx, and you would simply call that mass element dm. It's located at a distance x from the axis of rotation. Now if that's L over 3 and that's x equals 0, the left end must be negative L over 3 and the right end must be 2L over 3. So the first part we need to do is find the moment of inertia about the point, the pivot P. So I'll call this pivot P. So I sub P, by definition, is the integral of r squared dm. Now r here is the same as x because we are in one dimension. Now dm, what is dm? The rate of change of dm with respect to x is precisely lambda. So dm is just lambda times dx, where lambda is given to us. I'm going to omit the units, so it's 4x plus 3 times dx. Let me substitute. That's going to be the integral from negative L over 3 to positive 2L over 3 x squared. And for dm, I'll substitute here 4x plus 3 dx. Now this can be worked out. So when I integrate 4x cubed, I get x to the 4. And when I integrate 3x squared, I get x cubed. So that's pretty nice. From negative L over 3, and L over L is really 5, so that's negative 5 over 3 to 2 times 5 over 3, which is 10 over 3. And I'm not going to worry about working this out in front of you. You just try it on your calculator and you will get the answer, which is 157.4 kg meter squared. So that's part A. Part B, they want us to find the total mass of the rod. That can be done. The total mass of the rod is just the integral of all these elemental masses, dm's. So that's going to be the integral from negative L over 3, which I'll write as negative 5 over 3 to 10 over 3, of dm, which is 4x plus 3 dx. So that works out to be, when you integrate 4x, you're going to get 4x squared over 2, or 2x squared. And when you integrate 3, you're going to get 3x. And you substitute it between the limits 5/3 and 10/3. and that's going to be, again, I'm not doing the work, it's 31.7 kg. If you put it in your calculator, that's what you get. So now the third question asks us if the moment of inertia of this rod is larger than or smaller than that of a uniform rod pivoted about the same axis of the same mass. So let's try that first. If you had a uniform rod and not that rod that's not uniform, then what happens? Let's draw another figure. The parallel axis theorem has to be used, so this distance d becomes important. Remember, this is L over 3. So the distance d can be found. It is just L over 2 minus L over 3, which in an earlier multiple choice question we already saw. It's L over 6, or if not, you can do it here. The common denominator is 6, and that's 3 minus 2, which is 1, so it's L over 6. So by the parallel axis theorem, I'm going to get the moment of inertia about this axis through point P is going to be 1/12 ml squared, which is the moment of inertia of a uniform rod about the middle, plus md squared. So that's going to be m times L over 6 squared. You have to recall, and this is found in your formula sheet, the parallel axis theorem statement says that the moment of inertia about any axis is the moment of inertia about the center of mass plus m times d squared, where d is the distance between the axis and the axis going through the center of mass. So that's the distance d. Now let's try to solve this. That's 1/12 plus 1/36. So I can write 1/12 as 336 plus 1/36. That's a common denominator. 36 is a common denominator. ml squared, and that's 436, which is the same as 1/9. So now I just have to substitute. I sub p is 1/9, the mass, which is 31.7 from what I had there, times the length, which is 5 meters squared. And when I compute this, I'm going to get 88.1 kg meter squared, thereby proving that the moment of inertia for the non-uniform rod is bigger than that of the uniform rod with the same mass. This actually makes sense. The justification is, well, one justification is you did a calculation, but the other justification, the verbal justification, would be for the non-uniform rod, if you look at the density function, lambda equals 4x plus 3, clearly there's more of this mass for positive values of x, and for negative values you don't lose much. So you gain more for the positive values than you lose for the negative values. So that would be the justification. More mass outside on the positive side of the rod. And that's why the moment of inertia is bigger. Let's go on to the next long problem, which has something called a modified Atwood machine. It just means the traditional Atwood machine is a pulley with two masses hung from both sides. I think in one of the multiple choice questions you had that. This would be called a traditional Atwood machine. Now if the second mass is moved away from the vertical position, it's called a modified Atwood machine. So that's why this is called a modified Atwood machine. Now here, what you would have to do is draw the free body diagram. So let's do that. I'll draw it right on the figure itself. That's Fn. That's going to be mg. Then there's going to be some tension here, which I'll call T2. Well, by Newton's third law, equal and opposite T2. Now 3m is going to drag this down for sure. So I'll draw a bigger force here, T1. and equal and opposite force here, and then 3m is going to drag the whole thing down, so that's 3mg. Now as far as sign conventions are concerned, I'm only going to take the direction of acceleration to be positive and not worry about anything else. So for example, alpha in this case is positive because it's coming out of the page, and here you have the same acceleration a because the string does not stretch. So that's the free body diagram. For this one, for this mass, if I do the sum of all the forces in the y direction equals 0, I'm going to get Fn equals mg. Then sum of all the forces in the x direction equals ma. I'll get T2 equals ma. Let's look at this one, the hanging mass. The sum of all the forces in the y direction equals the total mass, which is 3m times a. Let's write that down. So 3mg minus T1 equals 3ma. So I have that. Actually, I can solve. Let me just keep this. I'll call this equation, I'll call that equation 1. I'll call this equation 2. And now we'll look at the pulley next. For the pulley, the sum of the torques must equals I alpha. Now both the torques, this particular torque is RF sine 90, and that is also RF sine 90 because of the 90-degree angle between the R vector and the F vector. But the directions are different. This torque is R cross F out of the page, and that torque is R cross F into the page. So that gets a negative sign. So sum of the torques equals I alpha gives me T1R sine 90 degrees minus T2R sine 90 degrees is equal to the moment of inertia of a disk, which is 1/2 mr squared from your formula sheet, moment of inertia table that is, times alpha. Now alpha is related to A by using the relationship between linear and rotational variables, and that is A equals R alpha. That important equation relates to 2. So for alpha, I can write A over R. So one factor of R disappears right here, and the other factor of R disappears like that. So I have T1 minus T2 equals 1/2 ma. That's equation 3. So now you just have to solve these 3 equations for whatever they've asked us to find. They've asked us to find the tension in each string and the acceleration. So we have to find everything. What I will do here is this. I'll put the 3 equations one below the other. T2 equals ma. That's equation 1. Equation 2 is 3mg minus T1 equals 3ma. And then equation 3 is T1 minus T2 equals half the mass of the pulley, by the way, is 2m. So I'll substitute 2m for that. Half times 2m a. So now let me add these 3 equations together. When I add them, that's a plus sign. That's a plus and a minus, so they all cancel out. So I get 3mg equals, let's see what we get here. M plus 3, which is 5 ma. Just want to make sure I did everything right. T2 is ma, and then T1 minus T2 is half ma. All right, so it looks good. 5 ma, and then if m's cancel out, that gives me a equals 3/5 g. Once I have a, I can find everything else. For example, I can put this in tension T2 which is m times a. So T2 is ma, so that's going to be 3/5 mg. So I know what T2 is. And T1, what's the best way to find T1? I guess this is not bad. So I can write this as T1 equals 3m times g minus a. So that's going to be 3m times g minus 3/5 g. So I can take the g outside. So that's 3mg, 1 minus 3/5, which is 2/5, or that's 6/5 mg. I want to quickly verify if everything works out. So let's just try that equation to see if it works out. T1, which is 6/5, minus T2, which is 3/5, so that's going to be 3/5, is equal to 1/2 m, which is 2m, so that's going to be just a, which is 3/5. Yep, it works out. So that's the answer.